Hi, this next video from the circles chapter is about tangents and chords. Before we start, just a quick look back at some useful circle properties that you'll have met at GCSE. So these can be helpful in some of the things coming up. First one, the angle in a semicircle is 90 degrees. So if you've got a line that's the diameter of the circle and you form an angle coming off that diameter, no matter where that angle goes, we'll always get 90 degrees. These will always be right angles. Okay, another fact, this wasn't one of the circle theorems, it's just a consequence of some of them. If we have a chord, CD, so this is a chord going from one side of the circle to the other, the diameter of the circle will always bisect that if it's perpendicular to it. The perpendicular to this chord will always bisect it. So in other words, the diameter is a perpendicular bisector of the chord. And therefore, it must be going through the centre. The third one is that the angle between a radius and a tangent that's meeting the circle at this point will always be a right angle. So we can form right angle triangles. That means you can bring in some trigonometry or some Pythagoras in problems involving tangents and radius. So those are going to be useful at various points coming up. So this part of the chapter is all about finding tangents to circles. We may have the equation of a circle given, or we may be told whereabouts it is, and we want to find the equation of the tangent. So the way we do that is we start with the normal. Now, because of what we just said about this being a right angle, if we have a tangent, the normal is at right angles to it, and we've just said that if you have a line at a right angle to a tangent, that would be a radius, or this whole thing would be a diameter. So the normal to a tangent is a straight line that follows the diameter of the circle. So that's going to be useful to us. If we want to find the equation of this tangent, we start with what we know about the circle. We will probably know the centre. We might know the point where the tangent is touching. So if we know these 2 points, we can find the gradient of this normal. Find that gradient, and then we'd know that the negative reciprocal of that would be the gradient of the tangent. So we would find mn using the centre and this point. The negative reciprocal would then be the gradient of the tangent. And then because we know, we'd expect to know this point that we're interested in, we usually know where we want the tangent to be, we can use y minus y1 equals n x minus x1 to find the equation of the tangent. So that's the procedure we'll be using. You find your gradient of the normal, because it's the radius, it's the diameter. Use the negative reciprocal of this, and then using this with the point of contact with the tangent into this form would give us the equation of the straight line. Then we may need to rearrange it into a certain form if we're asked for one. So let's see this in practice. First example, show that this point lies on the circle, and then find the equation of the tangent at this point. So first of all, showing a coordinate lies on a circle or a line or anything like that, it's just a case of substituting them in and showing that it satisfies the equation of the line or the circle. So we would start by substituting. Substitute x equals 4 and y equals 4. So I'm going to substitute 4 and 4 into here and show that I get 5. We could do it by substituting 4 in for x and then solving to work out y and showing that it's 4. That'd be another way, but this is easier. Substitute those in, we get 4 minus 2 squared plus 4 minus 3 squared. That's 2 squared plus 1 squared, which equals 5. So because we've got the 5 that we were after, 4, 4 must lie on the circle. Now that we know it's on the circle, we can find a tangent to it at that point. So in order to do that, we're going to need to find the centre of the circle so that we find the gradient from the centre to this point to then use the negative reciprocal. So I need to know the centre. Remember, the centre comes from the brackets. The centre for this circle must be at 2, 3. Then we look at the gradient of this to the point on the circle. So we've got a little diagram just to illustrate. 2, 3 is where our centre is. We've got something like this. The best circle. 4, 4. Somewhere up there. This is 2, 3. I want the equation of this tangent here. So we're going to start by finding the gradient of this here, the normal, then use the negative reciprocal to find the gradient of the tangent. So mn, gradient of the normal, changing y over changing x. So 3 up to 4 equals mn, changing y, changing x, it's gone up 2. So the gradient of the normal is a half, and that means the gradient of the tangent is -2, the negative reciprocal of that. And we've got everything we need now. We've got our m, we've got our coordinate. So the equation of the tangent we get from y minus y1 equals m x minus x1. We're not asked for a specific form, so this would be perfectly fine, though we might like to rearrange that into y equals mx plus c, since there's no fractions going to be involved. We'd get a positive 8 plus another 4. And we've got it. Equation of the tangent. Okay, number 2 is similar. It doesn't ask us to verify this on the circle, so we're just assuming that it is. We're finding the equation of the tangent to this circle at this point. So we need to follow the same procedure. We need to find the centre, but in order to do that, we need this in the bracketed form. So I'm going to have to start by completing the square. So I'll just go straight for it. Half the coefficient of x plus 1. Take 1 squared. And then half the coefficient of y plus 2 squared. Take away 2 squared. And then we've got the -21 as well. So I've got all the information I need there, but I might as well turn it into the standard form that we'd expect. So the bracket for x squared plus the bracket for y squared equals the radius squared. The length of the radius isn't of any use for this. We do need these two things, because we now know where our centre is. The centre is at -1, -2. So again, just a little diagram, not necessary. -1, -2. Not the best circle, but it suits our needs. 4 minus 1 over here somewhere. So we're looking for this tangent coming down here. So we start by finding the gradient of this. Radius, the normal. So from the centre, minus 1, minus 2, to the point we're using, 4, minus 1. Gradient of that, changing y, well, it's gone up 1. We're changing x, it's gone up 5. That would be the gradient of the normal. We negative reciprocal of that, it gives us the gradient of the tangent. And then y minus y1, etc. gives us the equation of the circle. That's the equation of the tangent. So y minus y1 at the point we're interested in becomes y plus 1 equals m x minus x1. And again, we might just change that into the standard form for a straight line. Example 3. I'm going to draw an axis here. I think a diagram will be useful for this. The diagram. Okay. So we've got, again, a tangent drawn from a point A away from the circle to touch the circle at the point B. Find the length of this tangent AB. So this tangent is going from this line, it's going to touch the circle at B, and I want to know the length of that tangent from A to B. So the way we're going to do this is similar to the start of the previous one. We're going to need the coordinate of the centre. So we're going to need to complete the square. Complete the square, half the coefficient of x, half the coefficient of y. I forgot to actually write here what I was subtracting, but you can do it at the end. So I need to subtract 4 for the first bracket, I need to subtract 16 for the second bracket, and I've got to subtract 5 at the end. For this one, I do want to know the length of the radius, because that's going to be used to help me find the length of this tangent. Okay. So I've got the centre of my circle at 2, 4. So out there. 2, 4. Radius of this circle is 5. Circle. Start here. So it's going to be something like that. Radius is 5. I've run out of space to show where it is. Bear with me. Okay, so there's 2, 4, the centre. 8, 2 is where A is. So it's over here and further down. Then a line is drawn from here to touch the circle. Let's just move to tools again and have a straight line. So I could go either way. I could go that way and have B at the bottom of the circle, or I could go that way and have B at the top right of the circle. It wouldn't matter, because another circle theorem you may remember from GCSE is that tangents to the circles from a point are always the same length, and that's what we're looking for. We're looking for the length of this tangent to the circle, so it wouldn't matter where we put it. We'd get the same answer. We'd get the same length. So I'm going to put it there. That means that is where B is, and I want to know the length of this line. Now we do this by creating a right angled triangle. Since this is the centre, this here would be a radius, centre to the edge. And we know from here that the length of that line is 5. We know this is a right angle, one of the properties we mentioned earlier. Radius and tangent meet at a right angle. And because I have this coordinate and I have this coordinate, I can work out, using Pythagoras, the length of that line. So using Pythagoras on this triangle here. This is the centre of the circle, call it O. We can find the length of OA using Pythagoras on this lower right angled triangle. Once I've got OA, I can then use Pythagoras again on this right angled triangle to find AB. So OA using Pythagoras, the base of this triangle would be 6 wide and the height would be 2. 6 squared plus 2 squared. Square root of 40. I'm going to leave that as it is. So this length here is root 40. Because now I can use Pythagoras again. Root 40 squared, take away 5 squared, and then square rooted would give me AB. Square root of root 40 squared be 40. Subtract, because it's a shorter side we're looking for, take away 5 squared. That's 40, take 25. That's root 15. This particular question doesn't ask for any particular form for the answer, so I'm happy with that. We could leave it. We could be asked for it exact, in which case we'd be there, or we could want it to 3 significant figures. So we'd have to use your calculator to get that. Okay, so that was a little bit more complicated. You have to spot that you're going to be using a couple of right angle triangles to solve that one. Next one. Looks like it comes from an exam, potentially. It's quite a bit more complicated. We have a circle, centre C. P and Q are coordinates given on that circle. M is the midpoint of those two coordinates, midpoint of the line segment PQ. And then we've got this line labelled L that passes through C and M. And our first task is to find an equation for L. So because of the property again that we mentioned earlier, we have a chord, we have a perpendicular bisector of that chord. If it's going through the centre, this must be a diameter. So diameter, chord, going through the midpoint, this must be a right angle. That's a consequence of the property from earlier. We must have a right angle here. So if we know the gradient of one of these lines, we know the other one is the negative reciprocal. It's that fact we're going to use. So we're going to need the coordinates of M. I'm going to use y minus y1 at some point. I'll have the gradient of this line, L, and I'll need a point that it goes through. I don't know the coordinates of the centre yet. I'm not going to use this line, this point rather. I need to know this point. And since it's the midpoint of PQ, that's straightforward to find. Minus 7 add 3 is minus 4, divide by 2. Minus 1 add minus 5 is minus 6, divide that by 2. We have our coordinate of m as minus 2, minus 3. So I'm going to be using that in y minus y1 later. I just need the gradient, so the gradient of L. Because I know PQ, P and Q, I can find the gradient of this one, the chord, and then the negative reciprocal will be the one I'm after. So PQ gradient first. Changing y, well, it's gone down 4. Changing x, that's gone up 10. Negative 2/5. My line L, the one we're after, is perpendicular to that. So it would be a gradient of 5/2. And now we have the two things we need. We have our gradient, we have the point it's going through. So the equation of L would be y minus minus 3 equals m x minus minus 2. Don't need it in any particular form, so to save space, I might just leave it as that. Otherwise, I would probably multiply by 2 and get it into the form ax plus by plus c equals 0. I didn't want to leave it in this form. Part B. Given that the y-coordinate of C, so the y-coordinate of the centre is negative 8, show that the x-coordinate is negative 4. We can do that because we have this line going through it that we now know the equation for. So we just need to substitute y equals minus 8 into L. So y equals minus 8. So we have minus 8 plus 3 equals 5/2, x plus 2. So it might have been useful to have rearranged this before. It's too late now. So this will be minus 5 equals this. Then I'm going to double it. So minus 10 equals 5x plus 10. 5x is negative 20. X is negative 4. So we've shown that the x-coordinate is negative 4. That's all we need to do for that one. Part C, find an equation for the circle. Well, we've got our centre now. So we'll be able to know the bracket part of the equation of the circle. All we'll need is now is the radius, which we could get in a couple of different ways. So we know our centre is at minus 4, minus 8. So we could put that into the brackets, x plus 4 squared plus y plus 8 squared. Now we could use Pythagoras, because I know where C is. Now we could use Pythagoras using CQ to find the radius, or CP to find the radius there. Or we could substitute one of these coordinates in, which is what I might do. If we substitute 3 minus 5 into here, we will work out what r squared is. That's what this is doing. It is working out what r squared is if we've got coordinates on the circle. So that's what I'm going to do. Substitute this x in, 3 plus 4 squared. Substitute this y in, minus 5 plus 8 squared. 7 squared plus 3 squared, so 49. 49 add 9, that's 58. So that must be what r squared is. Therefore, we have our equation of the circle, x plus 4 squared plus y plus 8 squared equals 58. And we're done. Okay, last example for this section. Circle C has this equation. So we know the centre and radius straight away. Given the line L is a tangent to the circle and has gradient -3. Find two possible equations for L in the form y equals mx plus c. So that little diagram might be helpful here. So the centre of the circle we can get from the two brackets, 5 minus 3. Radius is root 10. So 5 minus 3 somewhere here. Centre. Something like that. And then we want a tangent to the circle with gradient -3. Find two possible equations. The reason there's two is because we will have that one there. So imagine that as like a gradient -3. And it's a tangent to the circle. And then if I just copy that, so I've got another line with the same gradient on the other side of the circle. There. So I want the equation of both of those lines. I know that's 5 minus 3. Okay, all I know then is that the gradient of the tangents is -3. The consequence of that, though, is that I know the gradient of this normal line is 1/3. And I know a point that that normal line goes through, so I can find out the equation of that normal line now. And then if I find where that line intersects the circle, I'll have found these 2 points, which together with the gradient give me the equations of the two tangents. So the equation of the normal is where we're starting. Y minus the y1 we've got, it's a -3, equals the gradient of the normal, x minus x1, 5. So I might just rearrange that. Form y equals mx plus c, because we'll need to do a substitution to find the intersections. So I'll need this in terms of y. No, I'll need y as the subject. So 1/3 of x minus 5/3, take 3. That's 1/3 x, take 14/3. So that is the equation of the normal. The blue dotted line has this equation. I need to find these 2 points, so I'm going to find where that dotted line intersects with the tangents. So we're going to substitute. Substitute this for y in the circle. So this could get a bit messy. I've got my equation. So x minus 5 is going to stay the same. Plus, I need to do y and then add 3 to it. And if I just go back to this one, this is my value for y, this is my expression for y. And if I add 3 to that, this negative 3 just disappears. So I'm back to what I had originally, a third x minus 5 over 3. Just saved a little bit of time. What's on the end? Equals 10. Okay, so I've got to expand all that, get a quadratic which I can solve, find two values for x. Those two values for x will be my two x coordinates for these 2 points. Right, so x squared minus 10x plus 25 from the first bracket. And then when I square this, I'm going to get a lot of ninths. So just to make it a little bit neater, I'm just going to factorize the ninth out at this stage. So I would get x squared minus 10x plus 25 from that bracket as well. And then subtract 10 from this side, so it's all equal to 0. Right, I've got this ninth to deal with, so I might just subtract this 10 off the 25 first. So that now, when I times by 9, it's one less thing to times by 9. If I times these three things by 9 so that I can get rid of this one, I will get 9x squared. Take away 90x plus 135. And then this bracket now without the ninth on it. Don't need the bracket. Right, so I can combine these. 10x squared minus 100x plus 160. Right, thankfully that nicely divides by 10. And that factorizes rather nicely. So the x-coordinates of my intersections with my tangents are x equals 2 and x equals 8. This is x equals 2, this is x equals 8. I will need the coordinates, so I'll need the y-coordinates as well, so that I can use the y minus y1 again. So I'll need to substitute these into the equation of my straight line, or into the circle. Substitute them into the third of 2, take 14 thirds, would actually give me negative 4, and then substitute 8 in, 8 thirds, take 14 thirds, actually leave me with minus 2. So I've got the coordinates 2 minus 4, 8 minus 2. So those are the coordinates where the tangents that I'm after intersect with the circle. So those are coordinates on the tangents. I've got the gradient of the tangent. We were given that in the question. Okay, mt is negative 3. So all that's left to do is use y minus y1. I'll call this one L1, because there's two of them. Y minus minus 4 m x minus 2. And that becomes minus 3x plus 6 take 4. And then L2, second possible tangent, y minus minus 2, into 3 again, x minus 8. Negative 3x plus 24, take 2. Okay, so this upper one, if we wanted to put them on the diagram, I don't need to. This upper one must be negative 3x plus 22. So the y-intercept is 22. And this lower one must be y equals negative 3x plus 2. So my diagram should have been further right or further up, so that I had a y-intercept of 2. The diagram was just to help me, though, illustrate where things were what was going on. Okay, so if you're trying to find the equation of a tangent when you've got its gradient and the centre of the circle, we use the negative reciprocal to get the normal gradient so that we can find this blue dotted line and then find the intersections of that with the circle, because where that intersects with the circle is also where it intersects with the tangent. The tangents, once we've got those points with the original gradient, y minus y1 gives us the equation we were after. So that's it on tangents and normals. Have a go at the questions on this exercise and move on to the next video when you're ready.